Okay, so now just a brief little review about Newton's laws. So I'm really just today going to review the first law and the third law. The second law is just F equals ma. I feel like it's the one that we use the most. So I just wanted to talk about the first law and the third law, and kind of we'll go over some phenomena about those. But I feel like those are kind of the more secretive ones, the ones that are a little bit less common, and the ones that people don't really remember. So I want to go over those ones. So the first law, Newton's first law, is also called the law of inertia. Excuse me. And it's this idea that an object at rest will remain at rest unless acted on by an unbalanced force. An object in motion will continue with constant speed in a straight line unless acted on by an unbalanced force. So pretty much if we were going to boil this down to one idea, if the net force is equal to 0, there's no acceleration. Or just even simpler, things keep doing what they're doing if nothing interferes with them, if there's no net force acting on them. So if I put a cup on this table, it will do that until a net force acts on it. Because right now, if it has a balanced force, downwards force of gravity, normal force from the table, it's balanced out, and it's going to keep on doing what it's doing. So this law of inertia, so just kind of defining inertia. So inertia is an object's resistance to a change in velocity. So just how much is it going to resist a change? So if it has a lot of inertia, it will resist change. If it has a little bit of inertia, then it won't resist as much change. So when we were learning about inertia, I did this last year too, and it didn't really end up mattering. There's this idea that I skipped because I don't think, it seems weird. I don't get it. I never learned about it. It shows up in like the AP, like what you should know, but it just doesn't feel important, but whatever. So when we're thinking about mass, one of the reasons that inertia is important is because we can define this quantity called inertial mass. And inertial mass, the way that the College Board defines it, is the property of an object or system that determines how its motion changes when it interacts with other objects or systems. So when we use F equals ma, the mass that we plug in there is the inertial mass. It's telling us, oh, how is this object going to resist a change in motion? How is it going to resist an acceleration? If it has more mass, it will resist a change in acceleration. If it has less mass, it'll have a harder time resisting that change in motion. So yeah, that's our inertial mass. So if you just have like an object sitting at a table and you like slide it around on the table, you can feel how hard it is to kind of change its motion. I'm sorry, that's a horrific noise. I got this empty cup. It's empty now. I finished my tea. It's kind of difficult. This is kind of a hefty mug to change its motion. If I take something more lightweight, like this tape, it's pretty easy to accelerate. It's pretty easy to change its motion. I don't even know if you can see that or not. So it's pretty easy to change that thing's motion. So when we think about inertial mass, we can kind of think about, oh, when we force it, that's the mass that we were looking at. So if you move a force, whatever, so inertial mass, the mass that's associated with that F equals ma. And this is definitionally wise different than gravitational mass, which is the mass that's due to the gravitational attraction of objects. So when we dealt with this, when we talked about Newton's universal law of gravitation, this gravitational force equals g m1 m2 over r squared, this mass is telling us this property of how much stuff we're made up of, and because of this object's mass, it interacts with other objects. So right now, I just hoard mugs because I don't bring them to the dishwasher, but this mug has a gravitational attraction to this mug because these have mass. It's really low because they have low mass, but there is this gravitational attraction. Or if I have this mug, all these three objects, they have a gravitational attraction to each other because they have mass. Or if I thought I had more mugs, I don't. But so there's this gravitational attraction because of this mass, and that's really what we're looking at when we talk about gravitational mass. So how it interacts with gravitational fields. And so, why did we skip this? Because experimentally, if you were going to do an experiment, there would be no difference between gravitational mass and inertial mass. They're the exact same number. So it doesn't change based on how you measure it. For some reason, College Board makes a distinction. It doesn't show up too much. Sometimes they'll just say inertial mass, but it won't really matter. So it'll just be like, the inertial mass of this mug is 2 kilograms. And you're just like, okay, it's a mass, it's in kilograms. And that's really all where it shows up. But because they cut content down, I was like, oh shoot, maybe they're going to start nitpicking. So because of that, I just wanted to go over this. And then, so we got the third law. So the third law is conceptually pretty easy, but it's hard to apply, and people get it wrong a lot, just like in everyday life. So, well, not every day, but you know what I mean. Like if people are talking about the third law, it's common to get wrong, whatever. Third law, lots of ums. I'm very self-conscious now. So a force is an interaction between two objects. So in order to have a force, you need two objects. One single object cannot force itself. This mug can't force itself. I can't apply a net force on myself. I can't make myself accelerate just on my own. If I was out in space, I couldn't push on my arm and I wouldn't accelerate. I'm one object. So you need two objects in order to have this force. And then we're saying every force occurs as one member of an action-reaction pair of forces. This is kind of like the technical definition. So two members of an action-reaction pair act on two different objects. Two members of an action-reaction pair point in opposite directions and are equal in magnitude. So the most common way that people talk about the third law is they say, oh, equal and opposite forces. So really what we want to think about is this interaction between two objects. We have this force on one object caused by this object. I'll call this object 1, this object 2. We have a force on object 2 from object 1, and then a force on object 1 from object 2. Or I guess I could have done that with mugs, but you know what I'm talking about. Force on mug 1 from mug 2, and there's a force acting on mug 2 from mug 1, and those are equal and opposite to each other. That hoarding mugs is coming in pretty clutch. So if we're looking at a very common situation, hammering a nail, a very oversized nail, and a poorly drawn hammer, when they interact with each other, what we can do is we can do our force diagram just like before. We can circle one object, so we have these two objects in our interaction, the hammer and the nail. So we have the nail, we're going to circle it, we're going to say, okay, well it has this contact from the hammer, I see that that's crossing my circle, and I have a force that's acting on the nail by the hammer. And then if we look at this force pair, we say, oh, well I can circle my hammer and then say there's a force acting on the hammer by the nail. So we have one force on the nail by the hammer, a force on the hammer by the nail, and then these are equal and opposite. These are one of our force pairs. So we have this force on hammer by nail, force on nail by hammer, and this is an action-reaction pair. So what I want you to do really quickly, kind of to try this out, let's say a person stands on a box. The box is on the floor. Identify all of the action-reaction pairs in this setup. This is happening on the Earth. So what I want you to do is pause this video and give it a go on your own. See what you can do. See if you can identify these action-reaction pairs. There may be one more than you anticipate. But yeah, so give this a quick go. Pause the video here, try it out, and then I'll kind of go over it right now. Okay, so we have the person standing in the box, and yeah, what I want to do is just kind of identify everything going on here. So I want to identify all my action-reaction pairs. So what I'm going to start off with is the person, and just like I do, I'm going to circle my person, and then I'm going to identify the contact forces. So it looks like I have a contact between the person and the box. So I'm going to draw out really quick just to help me my force diagram. I know that I have this upwards force on the person by the box. I'm going to abbreviate these a little bit just to kind of help me out. So P is going to be for person, B is going to be for box. Then I also know that I have a downwards force on the person by the Earth. I have this force of gravity that is pulling my person downwards. Okay, cool. So I have labeled all the forces for the person. This is stationary, so I know those are equal to each other. And what some people would do, not saying you guys would do it, but what some novice physicsers would do would say, oh, well, these are equal to each other, and they're acting in opposite directions, so this must be a force pair. But that's not a force pair because they're acting on the same object. These are both acting on the person. So this is not an action-reaction pair. So I still have to find those. But because they're acting on the same object, they cannot be an action-reaction pair. Okay, next I'm going to look at the box. And with the box, the things that are crossing my circle, it looks like the person is crossing my circle, and the floor is crossing my circle. So if I'm going to look at all the forces acting on the box, I can say, okay, the keyboard is coming in. Go away. I know off the bat I have a gravitational force on the box by the Earth. So that's nice. And then I'm going to look at this and say, well, I know the person is kind of stomping on the box, so they're forcing it downwards. They're not lifting it up. So I also have a downwards force. So a force on the box by the person. Then if I look at this floor is supporting everything. So I can say, okay, I have this upwards force on the box by the floor. So if I'm looking at this, I'm going to start highlighting my pairs. I have a force on the person by the box that's going upwards. Why is that thing so small? So a force on the person by the box that's acting upwards, and I have a force on the box by the person that is acting downwards. So these are an action-reaction pair. We have a force on the box by the person and a force on the person by the box. So this is acting on one of the actors and the reactors. It's acting on the different objects in our force interaction. So this is a pair. I'm just going to number it. Oops. It's our first action-reaction pair. Okay, cool. And then the next one, the next object that we have is the floor. So if I'm looking at the floor, I can circle the floor and say, okay, we have a contact force right there. Technically, that also has whatever. We won't go any deeper with it. So if I'm looking at the floor, I can say the floor has a gravitational force on the floor by the Earth. And then there is a downwards force that is acting on the floor by the box. So the box is in direct contact with it. And then let's just say it's, we know that there's this upwards force also, but we don't want to like keep on going with it. We don't want to go like a bunch of steps further than we have to. So we know that there's this upwards force from whatever the floor is sitting on, like a layer of dirt or something. But we don't want to go any deeper. I don't want to label those. So I'll just say force on floor by ground. Whatever. Okay, so now if I want to look at this, I can start to kind of identify what I have. If I'm looking at my others, I have a force, an upwards force on the box by the floor. So that's an upwards force. And I just said, oh, I have a downwards force on the floor by the box. That is another action-reaction pair. So in this case, one of my actors is the floor. My reactor is the box. So I have this action and reaction between the floor and the box. One's going down, one's going up. They're equal and opposite between my two objects. And then I kind of have a bunch of unpaired things. I have this by the Earth, this by the Earth, this by the Earth. So what's weird is, kind of draw in the Earth here. It's kind of a very big, big box, big table. Whatever. Okay, so then what's weird is this idea that the person is pulling on the Earth, the box is pulling on the Earth, and the floor, those are all pulling up on the Earth. So yes, the Earth is pulling all these things down, but there's also an equal and opposite force from these three objects that is pulling upwards, acting on the Earth. So whenever you're standing on the Earth, it's pulling on you, but gosh dang it, you're also pulling on it, which is kind of cool. So those are really I guess I could call these pairs if I wanted to. I could say, oh, well, I also have a gravitational force on the Earth by the person, gravitational force on the box, on the Earth by box, I have gravitational force on the floor, on the Earth by the floor. And then those are all my pairs, but I'm not going to highlight them because whatever, you get the gist. Okay, cool. So that is that one. And then really the final thing that I'm going to ask of you is to look at this Google form that has you kind of looking back. I linked those videos and just kind of identifying, saying, hey, what force can get, but which Newton's law can kind of best explain it, and then just briefly justify why did this happen. So maybe if I'm looking at this cart one, I can say, well, those carts kind of stayed where they were at, even though the truck moved, so they kind of wanted to stay what they were doing. That reminds me of the first law: an object in motion wants to stay in motion, an object at rest wants to stay at rest. So a brief explanation can be like, oh, well, the carts, they kind of were all stuck together, so they had a lot of mass, which means that they have a lot of inertia. I know based on Newton's first law, this law of inertia, then the object at rest wants to stay at rest. So when the car moved away, those objects were massive enough that they wanted to stay at rest. There was very low friction maybe between the cart and the truck, so there wasn't really a net force acting on it. So the carts stayed doing what they were doing, which was being at rest. They stayed in place even though the truck moved, and then they kind of all fell out because they were staying in place. That was kind of a lengthy explanation, but something like that, just kind of saying, oh, well, this is the law, this is why this happened, maybe bring in, I kind of mentioned friction, so maybe bring in those other forces. And yeah, that's what I got for the day. So yeah, have fun.